Okay, in this lesson we will find derivatives of functions that have natural log, and let's look at some graphical evidence of what the derivative should be. So we can start with the graph of natural log, and we're trying to find the slope at every point along natural log. So I have x and y values for natural log, and we can see that here are the coordinates of that point, here are the coordinates of that point. We can use these coordinates to find to help us find slope. So we're going to draw a tangent line, just sketch a tangent line, and why don't we just assume that looks like it's about 1. So we have we're going to keep track of all the slopes here, and we have at x equals 1/2 we'll have a slope. At x equals 1 we'll have a slope, and we're going to say that slope is 1. Then we have to estimate the slope at 2 and the slope at 3. So let's look at a tangent line here, and we know one point on that tangent line is this point, and we just have to estimate another one. So why don't we say that this is the other point that we're going to use, and we're just going to estimate that that is 0 and negative 0.5. So if we have slope equals this is negative 0.5, so we're going to go negative 0.69 minus no, this is 0, and we're going to say that's about 1.4. So that's negative 1.4. That's y minus y. So we have a y value and the y value of this, and then we're going to have the x value, which is 1/2 minus 0. And we'll say that that is 1.42. So we'll say the slope of the blue line looks like it's about 1.42. And then we'll draw a tangent line here, and let's say that this point is 0, negative 0.2, and then we have the coordinates for 2, which are right there, 0.69. So the slope of the red line is the y value at 2, that's 0.69, minus the y value here, and we'll say that's negative 0.2. Then we need the x value at 0.69. The x value is 2, minus the x value there is 0, and we have 0.45. Then let's draw a tangent line here. And we're going to estimate that this is 0.2. So we're going to take the y value here, and that's 1.09, minus the y value there, we'll say it's 0.2. We need the x value is 3, and the x value is 0. So here we have 0.297. So let's put these slopes in the table and see what the graph of the derivative looks like. At 0.5, the slope of the blue line is 1.42. At 2, the slope of the red line, we have 0.45. And here we have 0.297. So at a half, we go to 1.4. At 1, we go to 1. At 2, it's about half. And at 3, it's about 1/3. So this is just helping us see where the derivative comes from and why the derivative is what it is. It's not a proof of what the derivative is, but if we just connected these lines, maybe that reminds us of we could predict what's going to happen to this line. Is it going to cross the x-axis, or is it going to be asymptotic? Well, let's think of what's happening to natural log. Does it ever go down? No, natural log continues to go up. So its slope will always be positive. It'll just be flatter. So here we always have to have a positive slope. And then let's look what happens over here with natural log. The slope is still positive. It's just getting higher and higher, more steep. So that means this is going to go higher. And that looks like a familiar function. And let's see what, since we estimated these values, what if we say that this is about 1/3 and this is about 1/2? We know that's 1. And if we estimate a little more, or stretch it a little more, we can see, well, that is 2. Maybe that's 2. If we see this pattern, 2 goes to a half, 3 goes to a third, 1 goes to 1, then it would be nice if 1/2 went to 2. Well, it turns out it does, and these are the slopes of natural log at these x values. So it turns out that the derivative is 1/x. If f of x is natural log of x, the derivative is 1/x. So we can see that here's the graph, or part of the graph of 1/x, and we have support for, or an understanding of why that happens. Okay, so here we have, when we do the derivative, if the derivative is the reciprocal of the argument of natural log, all we have to do is the reciprocal of the argument, and that means here we're going to have 1/x plus 2. X plus 2 is another function. This is composite. We do need the chain rule, so we do the derivative of the inside, and that's 1. So there's the derivative of a logarithmic function. Let's look at pause the video and try that one. So the derivative of natural log is the reciprocal of the argument 1/3x plus 1, and we could also call that the derivative of the inside times the derivative of the outside. If we do the derivative of natural log, we do the reciprocal of that, and then we have to leave the inside the same. That's what we're doing there. Then we take the derivative of the inside. Well, that's 3, so we have 3/3x plus 1. And we also have some, when we do derivatives, we can use the properties of logarithms, and that can make the work a little easier. So if we look at this, we can do this as, chain rule twice, or we can look at it as chain rule once because we get to move the exponent out in front as a coefficient. If we did it this way, that would be the outside, and then we have here's an inside which has an outside and an inside. So we have to do y prime is the reciprocal of this, and then we have to do the derivative of this, which is 1/2 x minus 1 to the negative 1/2 times the derivative of this, and that's 1. Just take the 1/2 in front. We have 1 over x minus 1 to the 1/2, and that negative makes this the reciprocal. So we had a negative, and that's in the numerator, so now it's in the denominator, and we can combine these. If we multiply these, we add the exponents, and that's just going to be 1. So there's the derivative. Or, if we did it this way, copy the 1/2, do the reciprocal of that, multiply by the derivative of x, which is just 1, and we're all done. Alright, pause the video and try that one. So we have, well, before we do the derivative, let's just do it the short way, and we're going to put the 1/2 in front. Then we can take the derivative. Let's go ahead and write it in that notation, dy dt. And the derivative of natural log is the reciprocal of the argument times the derivative of the argument. So we end up with 3/2. We put a 3 on top, and then 6t plus 2. And we'll just finish up with some equations of tangent lines. So for the equation of the tangent line, we need to find the slope, and then we'll do the point slope formula. So we need the slope at 2. That means we need the derivative, and why don't we rewrite that as f of x equals 3 ln x. So now we have 3 times 1 over x. The derivative of this, we're just going to copy the 3. The derivative of natural log of x is 1 over x. We have the derivative, and then we need to evaluate it at 2. So that's going to be 3 over 2. And then we do point slope. We know the slope. We know an x value. And then we need the y value at 2. That means put a 2 right there. So we'll have natural log of 8, and that is approximately 2.079. So we can have 3/2 x minus 3, because we're going to distribute the 3/2, and plus 2.079. Okay, find the equation of the tangent line when x equals 1. Pause the video and try that one. Slope, point slope. Before we do the slope, let's rewrite the logarithmic function with 2 as a coefficient, then take the derivative. So, reciprocal of that, and we also have to multiply by the derivative of that, and that is the chain rule. So we have 2 times 4, we have 8 over 4x minus 1. Then evaluate it at 1, because we need the tangent line at 1, we need the slope at 1. 8 over 3. And point slope. Before we begin, why don't we just find the y value at 1? That's going to be natural log 4 times 1 minus 1. So we're just substituting the 1 there. That'll be natural log of 9, 2.197 approximately. And then we can do 1 minus, or y minus y1 equals m, x minus x1, 2.197, and the slope is 8/3. The y value, or the x value, is 1. We're going to multiply by 8/3, multiply by 8/3, add 2.197. All right, and we'll stop there.